Hello, my name is Katina Michael. I'm from Arizona State University, and I'm the co-chair of the IEEE Socio-Technical Systems Committee of the IEEE Society on the Social Implications of Technology. And today I'm inviting you into my classroom, CSC 598 and HSD 598, Smart City Infrastructure and Technology, a funded core course of the NSF NRT, standing for the National Science Foundation National Research Training Fund. And we have with us a group of students from interdisciplinary spaces, inclusive of systems engineering, computer science, health management. We have sustainability scholars, design and architecture scholars, creative writers and science fiction writers, and a lot of computer scientists, different people from machine learning, big data and robotics. And it's a melting pot of students in their PhD predominantly, working towards the development of a care platform and multiple operational scenarios inspired by the work of Dr. Roba Abbas of the University of Wollongong and work I have co-led with her at Arizona State University. If you'd like to find out more about the NRT, please visit nrt.asu.edu. Now, the importance of bringing this to you today is an invitation to BrainChip Inc. BrainChip is a neuromorphic computer chip company that specializes in the neuromorphic computing sensors and chips that allow us to do things like inferences at a faster level and using simultaneous inputs coming through, both from voice, vision, and many other sensor-based innovations. And ASU has brokered this wonderful relationship with BrainChip Inc. It's called the BrainChip University AI Accelerator program, which provides hardware, training, and guidance to students at higher education institutions with existing AI engineering programs. And we're really excited to have BrainChip partner with us this year. They've generously given us their Akita 1000 chip, so that our students in our laboratory can run various applications and see how the machine learning could function with care-specific use case scenarios in the indoor environment, the outdoor environment, in-air environment, and also on-body operational scenario. And these are student-led projects which will inspire our next generation of care services, we hope, enabling novel use cases to demonstrate AI enablement. Our students who are participating in the program have access to these real-world event-based technologies. Again, thank you, BrainChip, which offer unparalleled performance and efficiency to advance their learning and graduation prospects. This is all about future careers. This is about using technology for good and also uncovering what some of those other socio-technical concerns might be, whether they relate to privacy, care, trust, and other social aspects. Also, the requirements for the environmental issues, that part that frames the social setting and the ability to use these kinds of machine learning technologies out in cities that wish to perhaps focus on health and care. So we're indebted to BrainChip for giving of their time and lectures during this session to ensure that students have the tools and resources needed to encourage development of cutting-edge technologies in their own innovations and in their own AI solutions. A final word from the IEEE. We hope you find this stimulating, this discussion and this presentation. I will precursor this. It's quite a technical talk. So if you haven't understood, for example, convolutional neural networks, CNNs, I'd go back and read about that, perhaps on brainchip.com's YouTube channel, and then come back and listen to this IEEE.tv. Do read up on neuromorphic computing, look at how it's changing the way that the traditional CMOS chips are working, and perhaps the advantages towards low energy costs in the future because they require less processing for the kinds of things that they're doing, and this push towards edge devices away from the cloud and away from heavy data communications, which are required in most IoT devices and most phones these days. So going towards something lighter. Okay, Katina Michael signing off now and introducing our guest, Todd Vieira of BrainChip Inc. and Nikunj Kocheta from BrainChip Inc. and from our class of wonderful students who are inspiring future visions of new innovations with respect to care. Thank you.
Thank you, Katina. Just to give you a little intro on myself, my name is Todd Vieira. I'm the Director of Customer Applications and Engagements at BrainChip. And we're a commercial company that deploys AI technology into the edge devices. And with me is one of our machine learning experts, our solutions architect, Nikunj Kotecha. So with that, Nikunj, can you put the presentation up?
Yeah, just let me know if my mic is working. I'm not sure if it's
It works fine. It works good.
Okay.
Thank you.
I'll just put the presentation slide.
So with that, what we're going to do is we're going to go over a little bit of BrainChip, what we do, how our technology is different than other people's traditional GLAs, and Nikunj will go into in-depth on kind of how we have a brain-inspired compute engine. So as I said, my name is Todd Vieira, Director of Customer Engagements, in Nikunj Kotecha. Thank you. Next slide. So today's agenda, this is the first of potentially 4 lectures we're going to give. We're going to go over introductions and overview of our technology, machine learning trends, the difference of neuromorphic computation. We're going to go over our MetaTF flow and give you some examples and then wrap up with any questions. If you have any questions afterwards, you can always email us or get in contact afterwards. So BrainChip is a leading technology company, and we are the first to commercialize neuromorphic technology. We have over 15 years of AI research with our founders, Peter van der Made and Anil Mankar. Peter comes from the neuroscience background, and Anil Mankar is from the AI semiconductor industry. And we are a world leader with on-chip processing and edge-based learning. And we have centers of excellence in the US, Laguna Beach here, France and India, and we have an advanced research and development in Australia. And we've had several big successes this year, within the last year with Megachips, Renesas, and Mercedes. And we've been profiled in various news articles. So one of the biggest announcements we had earlier this year was at CES. At CES, Mercedes-Benz has built an EQXX concept car. And this is one of the first fully electric vehicles to go over 1,000 kilometers on a charge. And they actually use BrainChip on the in-cabin monitoring system to do keyword spotting, the Hey Mercedes, and it was 5 to 10 times more power efficient than traditional AI solutions today. And currently we are working with them on next generation applications so that they have an overall systems efficiency that you cannot achieve in today's deep learning accelerator technologies. So one of the main distinguished points from BrainChip, if you look at traditional data center AI, you have these large, fully connected cloud environments. They're power intensive. You have unlimited compute, unlimited bandwidth, and you also have privacy concerns. As we see AI developing over the next 5 to 10 years, you're going to start seeing it distributed to edge point devices. And these edge point devices can be anything from doorbells, cars, industrial IoT pick lines, cameras, whatever. But those constraints are very different from having unlimited compute power at the, in the data centers. You have ultra low latency, you have bandwidth issues, you have real-time memory constraints on how much your device can handle at one time. And you may or may not have connectivity at the data center. So how can I do inferencing at the edge to have a highly optimized system that is efficient without connecting to the data center for inferencing. So with this, we have one of the first demos I'm going to show you. This is our what we call train demo, and this is going to perform some regression testing. And all our demos are located on our YouTube channel. So if you go to YouTube and type in BrainChip Inc., you can have access to a lot of different presentations and demonstrations we have available. Go ahead.
As infrastructure around the globe is aging, and the population on our railways, roadways, and in our structural infrastructure is increasing, the time is now to find better, more efficient ways to manage preventative.
Maybe having slight bandwidth issues. There it goes.
With BrainChip's Akita neuromorphic technology, smart city architects and managers can implement on or near sensor monitoring that is low power, low latency, and doesn't require connection to the cloud. By analyzing real-time regression in the vibration of these pathways, the ability to respond and solve issues before they would otherwise be known can dramatically increase the safety and security of those traveling these byways.
So just to let you know, this is actually a regression test that we ran on that small train that you saw. We had several vibration sensors sitting on those pillars and these little vibration motors that we could crank up the vibration and run it in normal operating conditions. Once you get over a certain threshold, we alert. Once it gets past the next threshold, we can say danger and then critical. And these are just one of the applications that in-house we develop in conjunction with some real-time imagery to show how we can use these in real-world applications. So as I said before, we're trying to solve the data and bandwidth problems at the edge, whether it's in automotive, whether it's home or consumers, or industrial IoT. What we're trying to do is increase system efficiency by starting at the sensor. And there's various types of sensors that are available, whether they're vibration, whether they're gustatory or vision or audio. Many types of sensors are at these edge-based devices. And what we really want to do is start by identifying what's the region of interest. In a lot of typical AI applications today, they're just sending tons of data, not only from the sensor, but to the ISP or the next side compute engine, and then it goes to the cloud. There's a lot of redundant data that's being transferred where 99% of it is irrelevant. And if we can identify what is important at the region of interest in the initial sensor data, and only transmit that data over to the next compute level and process that information, we are making an overall highly efficient system that addresses a lot of the bandwidth limitations as we get these larger and larger networks that are being developed for these cloud-based devices. So as we say, from sensor to inference, the key thing is I can capture data from the vision, audio, olfactory, gustatory, or tactile, any sensor. We can take that data, we pre-process it. As I said, we try and get region of interest. And then because we have a spiking neural network, which is different than traditional DLAs, we convert that with our CNN to SNN process on MetaTF. And what we'll try and do is run as much of that network we can at these edge-based devices where I have limited processing power and compute. And as much as I can run through the whole system on Akita, the lower power, the more efficient I can. Now, that doesn't mean we don't tackle more complex models, but that means as a system, I can utilize the CPU a little bit to do some of those early convolutions where they may not fit solely on Akita, which is how traditional DLAs run today. So I have a highly optimized computed infrastructure that allows me to optimize a system for efficiency. And one final thing here is with our BrainChip ecosystem, it's not just BrainChip on the compute side. We have several partners on the technology side, the enablement side, which is software and systems, on the sales partner side, and we have several universities that we're currently with. ASU is our one of our first people to enjoy the university program, along with Carnegie Mellon. So with that, I believe I am handing it over to Nikunj Kotecha, our solutions architect, machine learning expert.
Hey guys, very nice to be here. Before I dive into this, do any of you guys have any questions for Todd? You can unmute yourself and ask, or if you want to put that in the chat, we'll try to moderate that, and then we could, respond to those questions appropriately. Katina, okay. So what I'll be talking about is, building neuromorphic systems on, what we see as trends in machine learning, especially at the edge, what we are learning from biology, how we use those principles and apply it to one of our products, which we call Akira. So how we leverage those neuromorphic principles and combine it to make sure that we are running efficient algorithms at the edge. And then I'll talk about a little bit about how do we utilize Akita with MetaTF, which is our machine learning framework. And towards the end, what I'll provide is some examples of smart automotive industries, some other examples of event-based sensors, which might also be neuromorphic sensors as well. And at the end of the slide, we'll provide some sample data sets to look at. You could potentially do that for one of your projects if need be, leveraging MetaTF, learning, transfer learning, and going on, so on and so forth. So looking at trends in machine learning, if you see the bottom of this graph, you see the publication date, and machine learning has been here for a very long time, but recently in the last decade it has been expanding exponentially, and what we've noticed is shifting from the last decade, there is a lot of computation that has been involved, specifically with this deep learning architectures. We call this era as the deep learning era. And so with this computation increasing, you need to address, what are we trying to solve, at the cloud level, or what are we trying to solve at the edge level? And so there's another era where, we look at much more exponentially, compute, demand intensive, for one of our solutions, and then they can be like board problems or transformer problems or GRUs or such high levels of compute requirements that are the next level, but they demand a lot to be operated at the edge level. So when we look at this trend, and there are certain challenges that we need to face. Let's talk about the current approach. Talk about this pre-processing, and we have a lot of training involved, which involves using algorithms like backpropagation on our servers or these compute intensive machines that can handle all these algorithms, and then essentially we take these models, we take these architectures, and try to do some inferencing on an edge device, which may or may not have the same compute abilities, and so this is why it leads to some of the problems where in the deployment stage for these models at the edge, right? So you have a research flow or a training workflow done at the cloud level, but now when you make models for the edge. Even while training these models, you should be optimizing it for the inference level as well, and knowing what the target is, or knowing what device we would be using. There are certain optimizations that you could be implementing during the training phase, right? Now, there are other challenges, like in training, we typically provide, multiple samples together. It might range from batch size of 16, 32, depending on the availability of your resource. But when you look at the inference level, you're typically doing at batch size equal to 1 in most of these cases, and these could be streaming data, or some inferencing by just having an always on type of use case as well. So a lot of these problems needs to be considered and looked at from the software standpoint or from the development standpoint. And some of these other problems is, we look at the training data for these models. Now, when you look at the research world, it's meant for for you to go beyond and have a cutting edge in some of the models that you'll be developing. But when you actually go in the commercial world, or when you actually go in the production side, there's a lot that is restricted. There's a lot that is highly focused on the use case. So you may have a very simple data set to begin with, to work with, that may not even require such high extensive models to be used at the edge. Or you may have some heavy pre-processing to do so that you can really address even the edge cases that needs to be considered or handled on a commercial scale, right? So that is very much dependent on a use case application on a developer side. But these are some of the problems that we need to take care of when we are building models for the deployment stage. Now, there's another use case where we require an always on, or we require it to be computing very quickly, going back to sleep, or just be ready to provide a response, right? Maybe someone is entering a room, you need to have that solution in a security camera. You need to protect your vehicle from a theft for some cases, right? So when those happens, you need these engines to be super efficient, not consuming more power, while giving you the computation ability for these models that you'll be probably using for privacy cases or security cases, or just in general activating another larger model based on the responses that we get. And so for a lot of these problems, we think that neuromorphic is the way forward, because it can really address or take in these models applied at the edge, make the system very, very efficient, giving it lower power, lower latency, and the best scalability that you can get at the edge. So moving on to that transition, when trying to build a neuromorphic system, there are certain lessons that we always take from biology, and I want to dive in some of these key concepts. We hear a lot about this spike time dependent plasticity, which is SCDP in the neuromorphic world. So typically, it was first observed by researchers or scientists in the late 90s. And then essentially what it means is it's a phenomena that's observed in the brain, where each of the synapses, it's observed in the hippocampus. And so each of these synapses are very time dependent. So what I mean is, there is a pre-synaptic neuron and there might be a post-synaptic neuron, each of which, might be firing within, certain milliseconds. So for example, a presynaptic neuron might be firing, and after 5 milliseconds, you might have another fire in a postsynaptic neuron. And essentially what happens is that phenomena, we think of it as more as correlation, right? And it can be looked at as vice versa as well, where there is certain activity going in the presynaptic, and then after certain milliseconds, within the postsynaptic, let's say in that case, 20 milliseconds, you might have another fire going on over there. In that case, the weights of these different synapses might be a little different. Considering if you see the flow out here, uh, because the interval was so less, you have more information flowing and more qualitative information flowing in. And because this information, the time was, way too long, you might have less information flowing in. And so there are certain relationships that are, were observed or generated. And not just that, they also observe that you see a post synapses neuron firing before than a presynapses neuron as well. And so in some cases, you see at the bottom left of the quadrant, you might see these observations, and which is what it makes us feel that this is more than just correlation, and this is more like a causal implication that's happening within this SCDP phenomena that scientists observe. And so not just that, when you look at SCDP, it's diverse, but it's when you look at this processing in the human level, it just does not act alone. So what I mean is, there are certain relations that you keep observing. If you see the top right out here, you might observe certain patterns, excitatory or inhibitory, between the nature of these neurons. It might also depend on, the location of what this relation is occurring. And then also there are some neuromodulators like, that could create a different flavor of the relationship occurs between each phenomenon, right? Now, so when I mean by that SCDP does not act alone is because there are some homeostatic processes and homeostatic synaptic scaling that occur on each of these synapses. So what I mean is, we know that each synapses have a different level of weights that can, influence the result differently. But essentially, there is certain sort of these, processes that is basically sent in a form of a signal, and these are basically broadcast signals being sent from, one synapses to, many of these synapses out here to say, there are certain, because of different activity that the brain keeps on observing, it says that it sends this particular signal to all of these synapses to kind of maybe enlarge or reduce its importance in terms of providing or reducing its firing rate or increasing its firing rate for the next particular result, right? And this is something that is highly observed, on a brain, on a human level, and we take these lessons as, we do that in neural networks as well. There might be some neurons that don't hold much value, and we use these pruning techniques that can reduce its activity or reduce the dimensions, the layers or the channels for some reason, that can overall improve the performance of the model and can also be effective in the result that we obtain. So, when I talk about SCDP, it's really a very small portion of the entire puzzle, and a lot of it is also related to the memory component of it. So, in neuromorphic, there is itself its own memory component as LTP, which essentially can be looked at as multiple phases where it can really really be described in operations from seconds to hours, or operations from going on, hours to months, or a couple of years as well. So, there's a large variety in difference of, orders of magnitude out here. And when you look at SCDP, it's really more like the response time is more in milliseconds, ranging from 10 to 100 milliseconds. So comparing that to microprocessors, brain operates at a much slower rate than a microprocessor, but the opposite also true, where it's much more efficient in the way it processes than the different levels of microprocessors. And so, and this difference is observed in orders of magnitude, because there might be some stages where the learning might be a little tedious or longer, but because of these unique ability of sharing information from memory, or doing very, very local computation, it can provide responses very quickly, which is also something that is highly observed and should be learned or looked at. So when I talk about these lessons in biology that we keep on observing, and it's we still evolving, we're still exploring a lot of these stages within the human brain, and we feel this is still just a small component of it. But there are some additional lessons to just take away from this computation that we observe, or we keep on seeing, right? So think of like you're a mammal, either trying to get a prey, or escape from one, and so in that type of processing, you really need to be quick in response. You can't have years or long of processing, and so that's where the SCDP takes in effect. But there are these other learning mechanisms. You can think of it more like reinforcement learning, or you're constantly trying to learn, and you could do that over minutes, days, or even years for say, and those can be looked at within this homeostatic processes that take place. Whether it's in broadcasting signals to multiple neurons. Some neurons can learn very quickly. Some may take even a longer time, just depending on what type of mechanism are you trying to learn. And so essentially, when you look at these things, it is very important to see that not just the computation is important, but how are you doing this computation is equally important as well. So local computation, or doing in-memory computation, is something that is also being looked at and is being constantly developed by so many different research and scientists, because of this very phenomena that accessing is quick, but what if you access and just dump the information right there, right? And one last thing is about this neuromodulators, like dopamine. It could be very efficient and can be used as a broadcast signal that can be used in these learning capabilities. We looked at reinforcement learning or on-chip learning, which is what we have it on our chip as well. And so you're doing learning on as you go, and you're doing it very, very efficiently using all these phenomena that's occurring on a brain level, or a very broader level.
I think it's also important to understand, most traditional computers today, you have your, IO device, you have your separate storage or memory, your compute engine, and inside the brain, it's really minimizing the data path movement. So what we're trying to do in hardware is act more similar to the brain, because, the brain is one of the most highly efficient, optimized computer systems around. So by emulating how it's moving the data and it gets stored within the neurons and synapses, then you can do similar things on the compute side in a real world application.
So there were some lessons to learn, and neuroscience is obviously very interesting, but it's also very messy at the same time. And typically there are these three questions that come to mind is how does this SCDP algorithm fit amongst the different learning paradigms? There's a lot being said about it, there's a lot being researched about it, but two more important things is it really a thing, or is it really something that is observed? And so there are some experiments that do match with what we have observed, but there are also some that have completely different observations compared to what we should be expecting with this algorithm, right? And so on moving that further along, there's another question where, is it really the thing, or it's something of just as an artifact that we are observing, but at a brain level there's something really simple happening that we are not identifying, or we're not able to recognize at that point. So that brings that questions, but essentially personally I feel it may not be the thing, but it is definitely a phenomenon that we've observed, and there's a lot of research around it. It's something that should be used and looked at, but obviously the research should be ongoing on proving more out of it, and comparing it to different learning paradigms as well. So how we take some of these learnings and some of these principles and try to build out a product for commercial use is something that I want to share with you guys. Is SCDP is really interesting, right? But it may not be ready for its prime time, but it can definitely be used for today's machine learning algorithm, for today's CNNs and DNNs. We still have a long way to go for it, primarily because the amount of research and explanation for SCDP compared to these advanced algorithms like backpropagation or gradient descent is too much, right? Machine learning started in late 18s or 1900s, whereas SCDP was just recently discovered in the late 90s, right? So it's exciting, it's new, but there's something that definitely we could inspire into our product, and this, which is exactly what we did, is we inspire those events, or those information flow that flows from one synapses to the other. And so what we did is, for your traditional ML algorithms, we went ahead and we built some event-based algorithms that could complement that while leveraging these neuromorphic design principles. So essentially, we've built a neuromorphic chip that can take your conventional ML algorithms, and on the hood level, it can really utilize these neuromorphic principles and give you the benefits of both worlds, where you use these complex algorithms and CNNs for extreme training to get you the best performance in terms of accuracy or performance of these models, and then use this another world of SNN or neuromorphic, where it gives you the computation benefits like low power, low latency, ability to compute in very low bit precisions. So for example, we can take, we can have weights and activations of these algorithms anywhere from 1 bits to 4 bits. You can even do a mixed precision between the layers of an architecture. We've applied this event-based versions of these ML algorithms that really demonstrate how efficient a standard algorithm could be when being deployed or being worked on our Akira hardware. And I'll talk about that. I have a slide to explain that on how we do that. Learning from doing local computation, we do at memory compute. So there's dedicated memory assigned to each of these engines that we have in our chip. so that it can reduce these data movements for weights, or the event values occur from layer to layer, right? And we have distributed computation on our hardware, which really talks about how these engines talk to each other, how data flows from one part to the other, and they operate in in a parallel fashion as well. So you could really distribute an entire architecture across smaller different cores and have a really efficient processing done at the core of the heart. And so, moving on to that, we can take advantage of really running at very low clock speeds. So for example, one of our chips has the maximum clock is at 300 megahertz, and with that as well, we're really getting real-time performance for most of the significant architectures out there. And so it's really meant to really test out the neuromorphic performance, or to validate the compute ability at the edge, and it can really be scaled to to have larger clocks if that's something that our customers required, or it can really be targeted for a different fab technology as well, and I talk about that in the next slide. But really, our main product is our IP that we have developed, and the chip is really meant to be used as a reference design to kind of build something very quickly, or prototype some of your own models, and test out this neuromorphic technology. And one last thing I want to talk is this on-chip learning algorithm. So it's very much inspired by SCDP, and essentially what we do is we do this online learning, or of learning new things on the device, and we do that independently of the host as well. So no matter what host systems you'll be using, you have this online learning capabilities that happens on the chip, and it's really robust in terms of its capability to learn new samples on the fly, and I'll talk about that in coming slides as well. So this is just an overview of what our chip looks like, just for some of those guys who are really interested in it. Really the Akira neuron fabric is the core of our product, is the IP portion of our product, and essentially you have some other components to support today's ML algorithms, or to support how we can leverage these CNNs to SNNs. For example, the data processing and event generation really converts these RGB frames or grayscale frames to spike domain or to event domain that can be then operated on our IP. And the other components are just that are very standard in any ASIC, used for having data input interfaces, or just supporting the AI accelerator in general. But the key thing is, in our neuron fabric, we have 80 of these cores that I talked about earlier. So we have 80 engines, and these engines can be really used for any significant model, whether you have a smaller model or whether you have a larger model. We can allocate layers of different models to this respective NPs, and have the ability to compute at much lower power and much lower latency using the neuromorphic principle. So, when customers talk about the compute ability of our hardware, because we're IP, it's so flexible. It's very much configurable as well. So if you have a customer that looks in wearable devices, they might have restrictions on silicon area, or in the amount of memory and the TOPS that they really want for their use case. And then you might have these automotive grade industries where the focus is really on performance more than power compared to the wearable devices. And so we can really scale or have more engines allocated to address for performance, neglecting all the power advantages that it brings out. It just becomes more of a bonus factor when trying to compute it at those industry levels or those industry standards as well. So we really work with our customers, our clients to teach them what is neuromorphic, teach them how we can take their solutions and convert it. But at the same time, we also work alongside how we can address with our current solution, how we can address their use cases or their target constraints in terms of, let's say it's power, or whether it might be performance, or whether it might be both, having one trade-off over the other as well. So, having said that, when you look at Akira, and we get these questions a lot, what really is Akira? It's really a commercial product, really a commercial chip, which is used for deploying this ML algorithms at the edge level, or having the compute capabilities at the edge level. So with that, you might have certain constraints that you need to respect the hardware's boundary with, or you might have certain layer computations that may need to the assistance of a host to work in conjunction, or you could substitute with another layer to kind of have efficient deployment at the edge. What Akita is not is not primarily meant for research. You have other neuromorphic devices like Lowy and True North, which at the moment they have a lot of exploration, they have a lot of research, and it's completely fine because you need a lot of that as well. But it can't be they are within their own respect and where we focus a lot on the commercial aspect of how we can capture, or how we can keep leveraging the neuromorphic principles and providing the benefits of it at the edge level. So with that, I want to really talk about 3 different use cases or examples of how we are really incorporating these principles and targeting some of the use cases or the way we interpret some computations. So one being applying event-based versions of standard convolution networks, right? It could be just doing 2D convolutions. So when I look at what we do in event-based versions, if you look at the bottom row, when we implement this event-based convolutions, we're really taking into consideration of the events that are happening within the activation map, and this could be completely dynamic as well. You can't predict where would you be having these events in the activation map, and this is something that is so much of significant, because if you see, we still get the same result when we compare it with traditional frame-based convolution, which really takes the kernel over an entire activation maps, does some computation from centering each values and get some result, right? So we do get same result where we only take the kernel over the respective event values. In this case, it's just 3 events, so we're doing the computation 3 times, and in doing that, we see in this example we're doing much fewer max for the same computation that anybody else would essentially do. And this is something that is can be leveraged with today's architecture as well, because you have layers like ReLU's batch norm that really center a lot of these values around 0, right? And so when you do that in an entire architecture, you're doing that millions of times, and imagine you're doing 50% fewer compute. That reduces your power significantly and does give you a very faster computation as well. So another thing is how we leverage this neuromorphic and apply it to our to have the ability to learn on the device with one-shot learning or on-chip learning. And so the way we do this, CNNs are very good at feature extraction. So we leverage that. We think of this as transfer learning, but just with one shot. Essentially, we take the base architecture that is now converted to a neuromorphic world, to an SNN, and it is comprehended as a feature extractor, right? And so the last layer that really does the classification for a network, we replace that with our edge layer, which really does the neuromorphic learning, and essentially we can learn new classes, on the fly on the chip, or we can completely destroy the original classes. We can forget about it and just have the capabilities of learning new things on the fly. And so the reason why we do that as well is this allows for our customers to take this and apply it in the commercial world with use cases like device personalization, right? So for example, if you belong to a vehicle and you only want your family members to access the vehicle, you can really go keyless and doing this facial recognition or certain disauthentication factors and personalize the vehicle for your family, or have an in-cabin experience set up for individual members. Some might have a different climate condition requirements or seating requirements. So you can really customize it and provide that, that personalized, feel to your product for your customers as well. And so in other cases, you could probably use it in industrial applications where you have certain, on a conveyor belt, you're trying to classify certain objects already, certain products already, and you have a new product that's being launched. So instead of going through an entire hoops of training, making sure that now you make a new model that runs at the edge again, you can just implement this on-chip learning, learn the new product that you want to classify, and then start rolling your new product out on an industrial scale. That really saves up a lot on your cost in terms of the development, and really enhances your productivity level in an industrial scale. Another key thing that is really important is, because there's this sparsity within these activation maps that we could really leverage dynamically, there's this regularization effect called activity regularization that was initially developed to kind of make your model generalize a lot. It penalizes your model, to not being more sparse enough. And so it really helps the model to generalize and provide a good performance over your data set. So we could really use this for one of our approaches where this function could effectively make your activation maps more sparse. So on an average use case, you might have 40 to 60% sparsity because of these layers like values and batch normalizations. But when you implement, regular activity regularization in most of these models, in most of these practical models, it really enhances the effects and shows some benefits out there. So just to give a quick example of what I mean is, when you take a researchy data set like ImageNet, you have 1,000 classes to classify from. Traditionally, when you just look at, okay, I'm not doing this activity regularization, I just build the model for Akira and have it computed. The middle row shows that, okay, there's 55% sparsity and you're doing 50% less amount, almost 50% less amount of computation. When I apply activity regularization, there's not much effect because you really require a lot of that information in order to classify 1,000 classes. But now when I move onto a practical use case where you might have 20 classes to, in most of these applications, you might have ranging from 2 to 20 classes, you really see the effect of applying activity regularization, and you're doing much more fewer match than on an average case if you are not even applying a regularization effect, right? So in general, we are already doing less amount of compute, but now because you know what your hardware is doing, we can really take in these different losses or different computation that we do on a training stage, on a development stage, and build a model for the right target. In this case, it's Akira. So we know that it dynamically leverages the sparsity of an activation map. We can apply this toolkit, and it's available as in TensorFlow as a standard API as well. So you don't really need to build out a new algorithm for it. You can just apply it for your current models, for your current use cases, and leverage the benefits that we offer in terms of computation on doing it on Akita.
One question I had was on is Akita architecture different than the von Neumann architecture? And usually on the von Neumann, and I was typing it out, but you have your CPU, you have a large SRAM that it goes over to you have memory bandwidth you have to process as well. So so with Akita, because we have at compute memory, this whole neuron fabric here is comprised of engines and memory all together. So you're not reading and writing on a bus to where your CPU is managing the bus bandwidth, and we try and leverage not doing that, which makes it highly efficient both from a compute standpoint and a power standpoint, as well as a processing standpoint.
Yep, that's about right, Todd. And if you see on this, it's very fine print, but we have about 8 megabytes for this current configuration. And what it really means is because it has 80 engines, each engine, as I mentioned, they have a dedicated memory. So we have 100 kilobytes dedicated to each of these engines. But that's really configurable due to our IP nature. So if you have, hardware constraints, you could probably reduce the size of the memory. Or if you want to support, you don't have hardware constraints, but you want to support larger memory, that's also possible. But having local computation, we really learned that, it's not in memory, but it's at memory. So it does help a lot in, reducing the data movement, reducing the dependency on your overall system. And as Todd mentioned about this bandwidth, bus bandwidth requirements, other accelerators have a lot of dependency on that, and they need to write a lot of control logic to make sure that they are not taking away a lot from the system. With us, we do it everything locally. So we really are independent of this host system, and we allow the system to do any of its other tasks that it really needs to focus on, reducing a lot of problems or ability to really feed the AI accelerator the amount of information you need to feed to get the right latency that is really required. And we have seen a lot of use cases where this very problem of dependency on the bus bandwidth creates a problem of not being able to achieve the required performance for our customers. And so Akira really allows them to get the right target for whatever they're looking at for their
and one final thing, you talk about von Neumann, that's primarily done in CPUs. Remember, CPUs are based to do a lot of computation, but you have to write a lot of software with it. And it does one compute at a time, and maybe a couple as it's riding. Your GPU, that's for graphics, that's really meant to display 2D information that looks 3D. So it's trying to figure out relative to kind of the output you're trying to present in your gaming devices, very fastly determining where those pixels are located. So my game image looks very real depending on no matter where I'm looking or turning. It looks like a 3D image in 2D. So it has to have a lot of compute. That compute causes energy. And those are all von Neumann based, large compute engines, a large ALUs, a lot of memory. And at these, you know, and right now, I think they said by like, you know, 2035, a majority of these data centers out there, whether they're Amazon, Facebook, or anywhere, they're going to have so much energy being used. It's going to be more energy being used than 50% of the other energy uses in the electronics industry. So we are coming up with ways of doing these neuromorphic computation where we're trying to optimize these systems so you're not processing as much data.
Essentially for your RGB or grayscale, we've noticed that the front of the layers hold a lot of information or valuable information. And as you go deeper, the value of that information degrades. So we take in those 8 bits, and you can give even 4 bits if that's the pre-processing that you have done. It's completely possible. But we can take up to 8 bits, and then from there onwards, it keeps on shifting to 4 bits.
Okay, so basically you were saying we are using TensorFlow quantization aware training, or like you're just doing the post-quantized training, post-quantization of the trained model?
Yeah, there is no PQT, there is QAT. So again, that's an optional stage. And I'll dive a lot more deeper in the next lecture, which is going to be all about that, you know, how do we build these models for neuromorphic? What do we do with quantization? Talk to you about edge learning. So I'll dive a lot deeper into that as well. But essentially, if you're someone who is very excited and want to begin with MetaTF, so this is what I'm going to talk to you right now. So this is the software development platform, which is our Akita machine learning framework. And you know, you can access it through the link on the bottom.
Yeah.
Initially, you do get a form to fill out, but then you can totally access it. It's free for use as well. So this provides these Python packages for different stages. Okay, and I'll talk about these in more detail. But just to let you know, there are 3 Python packages: Akira, which is our simulator and also our execution engine for the hardware. CNN to SNN, that supports your TensorFlow models, quantizes them, supports the QAT efforts, and then converts that to spiking domain. And then Akira models is some of our own model zoos that we have developed and kept for you guys to like go and transfer on your data set to begin with. You know, these architectures are very optimized for our hardware. There are certain layers that might have been tweaked to address what works best on the hardware as well. And so that way, you can really get a head start in some of the use cases that you can target for. There's a lot of information, user guides, you know, examples of some of these processes. Like I think there was a question on how do we deploy something. So in examples, how do we convert to CNN to SNN? You'll have all of those, you know, nitty-gritty information on doing those. And if you're really familiar with Python and just developing, let's say in any framework, PyTorch even, you know, it'll be really, you'll be able to really quickly grasp on how to do things and then build something for neuromorphic. But in the next lecture, I'll really dive deeper into this framework, talk to you about edge learning, transfer learning, and just in general, you know, some tips and tricks to take care of in terms of when you're trying to build a completely new architecture out there. And for those who are interested in neuromorphic, true neuromorphic stuff, this also allows you to build native SNN. So forget CNNs and TensorFlow. If you're very excited to build native SNNs, you can do that. And you know, because we support spiking nets, this is a framework that you would use for Akira to build native SNNs.
When I compile the segmentation model with the Vela, I have seen that NPUs aren't getting, I mean, the segmentation models, just take an example of unit. It has not been performing on the NPUs. I mean, the processor which I used is 9MX, that is IMX 9M of NX space. So I have observed this when I have compiled using Vela optimizer. So I haven't seen that segmentation model isn't working better. I mean, especially some of the activation functions, and which are especially used only in the encoder decoder mechanism there.
So So the IMX9 is an ARM ethos based accelerator, which is not like ours. It's more of a traditional DLA. So totally different architecture than ours and how we do it.
Okay, got it.
Yeah, and so in terms when you talk about performances, right? So let's say you get segmentation, you do IOUs, so you probably get some X% of IOU for your model in TensorFlow. When you do QAT, you regain any degradation that you have. Now moving from then to your spiking nets, there is no degradation. It's just basically weight transfer of respective layers within your architecture to spiking neural networks. So the event-based versions of each of these layers. So we just transfer weights and you're not losing any accuracy or performance of your models in doing that conversion. And I'll talk about all that in the next lecture as well.
Okay. The last question I have is like you have DPU-RT and TensorRT and different type of platforms to convert your models to. And
Right.
this chip has an ability of getting model from any of the framework and deploy on it. Is there something like that we can do?
Yeah, that's a very good question. So, because you're targeting the commercial world, a lot of them use TensorFlow as a starting point, right? And so,
Yes.
which is why the first support is TensorFlow, which is why we have this automated APIs. But that being said, it's possible to take Onyx models, it's possible to take PyTorch models, and we have an avenue to convert those models. If customers come our way that they have an Onyx model, we support them. We have an avenue. We show them how do we convert that to spiking networks. It's just that we don't have an automated API because essentially at the end of the day, we take those weights for your layers and then we are transferring them to respective spiking neural networks layers. So it's just transferring those weights. So we have an avenue to support such frameworks, and we're constantly building MetaTF to have it automated as well.
Yeah, interesting. Thank you.
So that's with MetaTF, and I'll talk a lot more in detail about that in the next lecture. But I'm really excited to show some examples that some of our partners have done, and we have also demonstrated some capabilities along with our customers. So one, this is Enviso. I think Todd talked about this in the beginning. They are our solutions partner, and they develop solutions, for multiple different avenues. This one is for in-cabin. So they have an entire ecosystem for in-cabin where they're running multiple models, within their SDK. So originally they were doing it on the NVIDIA Jetson Xavier. If you see the image on the top left, and our reference board, which is a PCI board, they were able to port all of their models using MetaTF within like a day or two. So it's very easy for them. And then they plug it to that NVIDIA board just to act as a host, just like a Raspberry Pi. But then all the neural network inferencing is happening on our chip out here. So I'll play the video and you'll be able to see there are so many models like pose estimation, gaze estimation, etc. that they're doing one after the other, but it looks that they are doing it in parallel.
Is labeled as driver, co-driver, passengers, and so on. Then each driver independently, it's analyzed for facial landmarks and head pose, which are needed for the whole system. Also emotions, age, gender, and face identification.
Okay, and that's coming from a camera inside the car?
Yes, the camera is up here.
Okay.
Connected to the board, powered by the car system, and also a screen for.
So when I show this demo to some of our customers, they get very excited along with the numbers, the benchmark performance that we give, is because on the NVIDIA board, you typically burn a lot of watts of power, and in this specific one, they were going beyond probably 10 watts of power for the models that they're trying to run. When they shifted to Akira, now they're trying to burn just milliwatts of power. So that's a huge gain, especially for the automotive industry, because now they're going into EVs, There's a huge demand on making, your cars, very efficient in terms of battery consumption, making them long range and all. So having all these computation done at the edge level with such low power is something that goes beyond. It's something that speaks for itself, and it's something that our customers are very excited. The Mercedes article that you saw, 1,000 kilometer might not just be because of neuromorphic, but it is one key component that helps them to reach that efficient number that can really make their product a cutting edge of that. Another one that this is something that we have done as well. We've leveraged our edge learning example. So the one on the left that you'll see will recognize who the person is, and we've learned them on the fly for before this recording. They will speak just like any other detector. They'll speak, "Hey Akira," recognize them, verify who them as well, and then on the right is kind of an always on type of model where it could be used for security, theft, or anything where you have someone being recognized, or you want to do child protection in the car as well. That's also a possibility. So these type of models are always on, and they require much lower. If they are gonna be always on, you don't want to burn watts of power. You want to burn probably microwatts to milliwatts of power consumption. So I'll play this video, and hopefully the audio and everything comes in smooth.
Hey, Akita.
Aaron, all systems active.
Hey, Akita.
Todd, all systems active.
So you saw we were able to, apply even this edge learning, make sure that, okay, it only activates the vehicle for Todd, even though he pressed it, but could be very smart in the future as well, right? Maybe Aaron is one of his kid and doesn't want it to be activated, because it's his family member entering. There's another demonstration. Now we saw with, RGB, we saw with audio domains, but let's look at this event-based sensors. And so IBM DVS 120 is a data set that it's available publicly as well. You could even go ahead and download it. But what essentially it has is, it basically has samples of people doing different gestures, and the recording is done through a DVS-based camera. So when we build these, architectures for Akita, one unique thing about here is now these cameras are giving you event values directly. So the component that I showed for generation of event for RGB or grayscale is completely skipped on our IP, right? So you can directly take these events, pass it into Akita, and then skip the part of making a frame or converting or going so on and so forth, right? So if you look at it, any other accelerator, even if you provide these event values, they would have to create some sort of a frame and apply traditional convolution, traditional operations on it. So I'll just play this demo video. You'll be seeing he's going through different gestures, and the sensor is so quick in getting those values, and we are also very quick in computing each of these values that you're also getting. If you see the bottom right, the latency for every sample that we process is under 3 milliseconds, right? So this is something that is also very useful for automotive, is also very useful for many medical use cases or even industry use cases, where you have maybe predictive type of tasks. You want to predict something that is very quick. You want these automotive vehicles to be very robust, that an RGB frame may miss, but an event-based camera may not. Or if you want to have in the industrial scale, if you have these conveyor belts where you have very fast-moving objects falling through, and you want to count them or you want to recognize them, event-based sensors will help you over an RGB frame sensor as well. So Akita is flexible, it's domain independent. If you have an event-based camera, Akita is the best fit for it, okay? Because just you can take these events directly. If you do have an RGB sensor, we have a avenue where we convert that into spikes and still demonstrate benefits of using a neuromorphic approach for all of these different modalities and domains that you might be seeing. And if you go to our YouTube page, you'll probably see a lot more demos. We'll see probably with drones. We'll see we're tasting beer with Akira. So we have this chemical compounds where we recognize different reactions that occur, and we are able to capture different properties for these beers with Akira as well. So when I compare this exact model with public information that's available, so with another neuromorphic architecture, True North, if you see, they get about the same accuracy. And essentially, we've not even tried hard in optimizing the model. We just went for it with a standard pipeline. But the key difference here is when you see, they're using a model with 18 million parameters, and we just use it with 138,000. That's a huge in terms of computation, which you can see right in the next two rows. They're using about 96% of their engine, and we're just using 9% of our engine. That really accounts for this low power that you can see in the next row, where we are significantly lowered in consuming the amount of power that we take for this particular model, right? And in terms of accuracy and training, it's all dependent on how efficient you are in these development flows, or you may have custom losses that you can write in TensorFlow. So you can leverage the benefits of CNNs in training, and then benefits of SNNs in really the inferencing moment of your. So to kind of conclude, hopefully I was able to demonstrate that there are a lot of these opportunities that you can take an advantage with neuromorphic computing at the edge, and it really complements your current architectures, your current ML architectures that you might be using. And essentially, if there are these other use cases, that there are many applications, you could probably encode some information, you can encode some temporal information as well, and really take the advantages of a neuromorphic hardware. And as I mentioned earlier, we're taking best of both worlds. We support CNNs for your training. You do what you do best today. We take that and convert that to SNNs for inferencing, leveraging the neuromorphic principles. And then when I talk about these lessons in biology, there's still a lot to go. I mean, we're still exploring, humans are still exploring. There's a lot of research going on, especially with this, broadcasting that we do. And is it really the computation that we are observing, is it really happening or not? So there's a long way in order to make this the absolute perfect, but this is a good step forward in making the next thing out there, making the next revolution device out there that is biologically inspired, that is inspired by a lot of what we do today. And we don't need to really build really heavy power consumption or really heavy architectures, accelerators that can address what you need to do. You can really inspire a lot from biology. And I think I have some slide for you to maybe look at some data sets if you want to, for your projects that you'll probably do in your semester, or if you're really excited in challenging yourself and looking at the next thing. We're open. We're really excited to see what you guys can you guys come up with some of the projects. If you need, we can discuss some of these projects and maybe the projects, or to do these, you can send me an email, see what you have to think about it. It's we'll be open to it, but just kind of a reference out there. These are some of public data sets that we've already worked on, and you could also really work on and build something really extraordinary out there that even beats some of the models that we have made and leverages the neuromorphic hardware. So with that, I think I would conclude. I think we are almost at time. We'll be over time, I think. So if you guys have any more questions, I'll be happy to answer them. One thing, I'll be going into the MetaTF lecture, framework much in deeper for the next zone on really how to build stuff for Akira. So if you have questions beforehand, shoot me an email, or maybe you can bring it up. But if you want, it could be a really nice thing to go over there, check some examples, get a head start on moving forward with that.
Yeah, I think it's really important. Next time in about 3 weeks, I think we're scheduled for. We'll go over MetaTF. We'll go into a lot of details. I think I'll repost the link inside the chat. So if you guys want to go there as well, you know, it has users guides. There's how to use the models. There's examples. A lot of different you know, things can be answered there. And if you have any questions, I think we'll provide both of our email. And do you guys have any more questions? I mean, it's a lot of material to go over, and we're trying to, you know, divide it up into a couple sections. Where the first one is about the architecture and what we're doing.
We do have questions, Todd. We had estimated another 20 or so minutes with you at least, but only if you have time today.
I have plenty of time.
Okay, I'm going to hand over to the students, but just give you a bit of a backdrop. Perhaps Lance or Diver, you wanted to introduce the project that we're working on broadly.
Sure. So, hi, I'm Diva. I'm one of the public policy students working on the team. So we're creating a care platform. We're really interested. So we have expertise from a few different areas. We have healthcare students. We have a lot of computer science students. So we're trying to integrate how we can create care in ideally a place-based community. So maybe in the Phoenix area, something like Tempe, potentially on an issue of urban heat, with specific focus on communities of unhoused people. So those who are specifically impacted by heat, and how we can integrate our computer science students to use the Akita chip to create care solutions for those communities and for those issues.
Did anyone want to add to that broad, concise project description?
I think that's very exciting. You know, with this low power energy consumption, you know, a lot of our customers do think about it, and then what you're doing in the medical space or in this health science space is something exciting. I'll be looking forward to what you come up with most of these use cases.
Yeah, just to let you know, we have use cases that come in from the whole gambit. We have NASA working with us. You know, they can't really tell you what we're doing, but they're doing things. They're trying to realign their outer space things to recognize stars to get orientation. You know, as we said with Mercedes, they're doing device personalization in cabin. We have customers that are using it for, you know, just identifying men and women in these gaming rooms to figure out which machines people like doing gaming on. So, I mean, we have it in the agricultural industry and the farming industry to recognize different sounds from animals that have, you know, sickness, because they make different sounds relative to the healthier ones. So they can, you know, if they find out which bins have sick animals, they can take them out before it spreads to the rest of the crops or the rest of the herds. You know, it's all over the place.
Yeah, it's really exciting. And I think like we're really early in the ideation phase of trying to figure out like, okay, we have to contact stakeholders, do an IRB application, and just to think of all the different inputs we can create, and then like what mechanisms and what models are we identifying. It's overwhelming in a very exciting way.
Yeah, you're doing the right thing. Do map out what your intent is and focus on the end goal, and identify each component. If something is really taking a toll, maybe there's a way around it as well. But yeah, you know, do map out before you begin, and every stage is important for your project. So.
More questions?
Is there any chance to add blockchain technology in this industry, like combining with AI and like recording data and stuff like that?
I think if you're talking about combining different industry, I think it happens always. We've give you an example. You know, there was a customer who was looking at doing data analytics, but they initially want AI at the beginning to kind of filter some of the data that they are getting as well. So there are many industries that you could probably combine together, and this is one classic example. Maybe going in a region where you don't have internet connection, or you don't have, you're there for a very long time. Let's say it's in a forest or something. Having this compute ability at the edge, and you do allows them to filter a lot of unwanted noises from, let's say, animals or species that they don't really want. At the end of the day, it helps them to burn less, have the ability to capture more, and do more computation, or avoid the post processing of those data analytics that you would essentially be doing in a traditional way.
So blockchain technology, I think it's, as I heard, that is good technology for storing data, and as you said, AI helping to analyze this data. Adding blockchain technology with AI, it's gonna help to analyze data more easily. Is that correct?
I think so too. Yeah, I think it would be definitely beneficial. More information. We do support this online learning ability as well. So having, like I said, the filtration, or having the ability to do something on the device is beneficial in many of these use cases.
Just a curious question, not a technical question, but like when you say these benchmarks on power consumption and how these Akita chips help to be more or less the same accurate, but with so less minimum power consumptions in watts, milliwatts. So, and it's kind of a follow-up question on what just Mohammed asked, is like, for example, cryptocurrency as an industry has taken a lot of hit because how exhaustive and how it's not in aligned with the green computing as people are trying to move forward with. So just curious to know, have you guys did any kind of analysis over there that how your chip can, again, maybe give a boost back to cryptocurrencies and digital currencies, which has basically been facing problems due to green computing?
So normally, we have all these benchmarks that we do, and we run different ones that show different customers. I'm sure if you go to YouTube, I'm sure we have some of them there. Generally, when we have customers we talk to, we have NDAs that we sign. So this one's more of a generic information, but I know we put them up on our YouTube channel as well. But we do, we are seeing quite a bit of lower power and compute optimizations for a lot of these networks in these arenas. And one of the things that you guys don't really get into on the hardware side is, if you're familiar with any of the technologies that are being manufactured right now, this isn't a fairly old technology. It's a TSMC 28 nanometer, and that's a very mature process, low cost. And people like Apple and Qualcomm, who are building their next generation SoCs, they're down in lower and lower technology. And by taking our engine and integrating it into these lower technologies, you're going to have X percentage lower power and higher compute. So the ML is just the one side. The actual hardware implementation is the other side. And we are what we call an IP vendor. So we license our technology to chip companies, and they integrate it into their next generation chips. But since it's a newer technology that's meant to be disruptive, we have to prove it out before people will use it. Similar to like an FPGA, but FPGAs have limitations on how you can do at compute memory because it's not really made for that. That's why we have the test chip available in these factors of PCI Express, and we'll have USB later on this year.
So if I understand correctly, maybe in the future we can have we can see some integrations into like NFVs as well, like in network devices, in routers as well, where it has nothing to, maybe their primary objective is not ML applications, but maybe a better routing of packets instead.
Yeah, so in all of these use cases, there are tons of networks that are used. So for example, enhancing a signal, or removing the noise from the signal. You have networks that could do denoising. You have networks that could do enhance it, just using the encoder decoder approach. Or even in the cyberspace, there might be anomaly detection algorithms, or there might be cybersecurity based networks that really needs to be always on, and it's always trying to detect for some changes, or you need to learn the activity that's going on with your security. So you could leverage this online learning feature as well. Apply some reinforcement learning. uh, Make sure you're kind of improving your model over there. So yes, there is a lot of scope. It's just, I think, uh, as the decade moves forward with more of the edge device or more the edge computation, you'll see more of these happening. And I think we've already seen this. There's a lot of improvements on your phone cameras with just simple denoising of your image resolution, right? It could very well be applied to even signaling, or maybe it's RF signaling, or maybe it's infrared, or you have LiDAR coming in. So we have customers reached out for all these use cases. We are working with them. Uh, it'll come soon. It'll come. We'll see these integrations in products very, very soon.
And we already have like our first customer we licensed to, it was over a year ago, Renesas. They should be coming out with, it takes 2 or 3 years to develop a chip. So they'll be the first ones that have something out in mass volume, probably at the end of next year sometime.
And Nikunj, is MetaTF framework is similar to Edge Impulse, or like can I assume something similar to it?
Yeah, good question. So MetaTF is not similar to Edge Impulse. You could think of it more like TensorFlow. It's inheriting a lot of TensorFlow properties, and has some abilities to support your 4-bit quantizations and conversions to SNNs. Edge Impulse provides a nice tool for you to collect data set, prepare them, pre-process them, build out models, train them, and finally deploy it. Maybe use AutoML for certain optimizations. So they're two different infrastructures. But that being said, we've also partnered with Edge Impulse to have developers like you go on Edge Impulse, who are very heavy users of Edge Impulse, can build out models that they have, and build models specifically for BrainChip Akira. So essentially, you still go through the same flow that you do with Edge Impulse, and then there is a deployment stage where you'll see BrainChip MetaTF, and we're still integrating a lot of these features, but we have a path with Edge Impulse that, coming from Edge Impulse, you can build these neuromorphic models and also deploy it on a specific hardware if you need that amount of support.
Yeah, so we signed an engagement earlier this year. We're working on the integration. So as we go through the rest of the year, more and more of it will be integrated into Edge Impulse to make it easier for developers to use our hardware.
Okay. So, Nikunj, I have asked the question, Intel Mobius NCS stick, neural compute stick. So which it's like acts like a deep learning accelerator kind of thing when you connect to CPUs. And can I think like BrainChip, as you already answered the question? The question here is like, can I use this, like, can I think this BrainChip chip as like, can I connect to CPU and run the deep learning inferences on the chip? Can I do something?
Yeah, definitely. Akira is a neural processor. So you can think of it as a accelerator for your neural networks. And at a chip level, yes, we have this reference board. You can hook it up to a Raspberry Pi, Xavier board, or other Linux systems, and really use just Akira as a tool for accelerating your neural networks. And then because you are IP, the IP portion gets integrated inside a chip or a module. That's a different, avenue. But for you guys, yes, I think the university has certain systems already. It's the same concept. It's hooked up to a CPU, and you're using Akira as a reference board for your acceleration.
What is the size of dimensions of this chip? How much big it looks like? I mean, is it very big or small? How does this look?
It's the size of a quarter. If you know what a quarter is, if it's the size of a quarter. It's very small. And currently the interface is with PCI. And so if you know the form factor of M.2 boards, it's of a similar form factor on the PCI board. So it's a mini PCI board, which has a chip on it.
Yeah, on the board, it's about 1 inch by 3 inches. So that plugs into your PCI slot on your server, Linux-based server. I'll be shipping those out. We'll be shipping those out tomorrow. So your team can have access to them in a week or so after they get implemented on the system, the host system that you'll be using.
Yeah, sure. Thank you.
So PCI is just an interface that we use for, your data movements and fetching the weights originally. As I showed you the block diagram earlier, you have interfaces like USB, I2S, I3C. And so, you could really, if your customers are familiar with developing boards, they can take just our chip and build their own custom board around it. So however they like, whatever components they want on it, whether they want certain DRAMs or XYZ components, they could build an entire module out of it.
Hi. So earlier in the presentation, you touched upon how our microprocessor are much faster, but the brain is more efficient in dealing with compute problems. So I was wondering if we keep building towards replicating the brain's efficiency, would we eventually be able to match that, or would we run into a bottleneck somewhere down the line?
So right now on the compute side, they are running into a bottleneck with von Neumann architecture because you have separate memory, you have separate buses, you got all these IOs, all these different things going on. And your CPU, when it's doing the activation, it does, and I think I said this before, scalar-based computation. One thing really fast, your GPU will do vector-based computation. So it does one full line of multiplication accumulate, because they have lots of ALUs, but each one comes with a different inherent problem, but they all do computation the same way. When they are computing these activation maps, they're computing all ones and zeros, and anything multiplied by a zero is a zero. This neuromorphic approach bypasses the computation of the zero values, therefore reducing the computation by 50%. And then the other thing we do with 4-bit quantization, remember, if you have 32-bit memory storage, you have to have area to store those 32 bits. Even at int 16 or int 8, you still have to have twice as much memory. So when we do 4-bit down to 1-bit quantization, a 4-bit only holds 16 values, 0 to 15. And so you're trying to say, I have a constraint-driven system that's either battery powered or low energy. I can't have unlimited compute and processing like I do in the data centers.
Yeah, and this is supposed to be, there are ways around it. I mean, this is with respect to the hardware, but also on the software level, we need to start looking at stuff with quantization, building lower bit precision models. Now I showed you earlier, there are larger models in place now that are very good in computation, but there's at the edge level, you don't really see them being applied because of the amount of compute it requires, right? And so there is a a wall that these guys are hitting now in terms of scaling down to lower technology, adding more and more compute, you need to start thinking differently and smartly, and which is what everybody is now shifting to, is making more, biologically inspired chips. You have these vendors or these companies trying to implement analog based computation, right? So if you are familiar with analog, it's, in order to make it as a chip, it's very unstable, but essentially it is very low power consumption, because for neural networks, a variation is okay in passing signals. And so computing in an analog domain is very efficient for neural networks. So you tend to think smartly, you tend to behave, inspire a lot of things from what we are doing today. And I think, to conclude, if we will reach the level of the brain or not, I don't know. Let's see in the future. But we are definitely getting one step closer. We are way far ahead than what we were in late 90s, and we are speeding up rapidly anyway. So
the other thing that's important to remember too, technology to make a chip, I think at 28 nanometers, about $50 million to make a chip, verify it, put the infrastructure in place. To make a 5 or a 4 nanometer chip, it's $500 million. It's just exponentially, more expensive to do lower technologies. That's why you only see, primarily the large, Apple, Samsung, and Qualcomm, the large volume guys that are doing high compute chips can afford to do it there. A lot of the other guys just don't have the money to sink into that. So you're going to need, these new ways to build chips, more efficiently and cost prohibitive, and cost won't be prohibitive down at the lower technologies.
Just on that point, I have an important question for, I guess, representing our systems engineers. We've got quite a few of them. They specialize in robotics, in AI, and one big data is another one, but they're systems engineers, so not necessarily the skill set of our computer scientists. Can you bring our systems engineers into the picture? Do you need how many of these Akita boards when you're deploying what kind of system? For example, let's just say I created a concept like a care platform that would monitor everyone in my point of view. Say I'm a lamppost and I'm in a city infrastructure. Do we need one Akita that does the inferencing by collecting the data from the sensors, taking it back to the cloud, or do we require one Akita per lamppost? Just give the students a bit of a understanding. Do we need 4? Is it density driven? Is it capacity driven? Congestion? What is it?
I think it's going to be a little bit of both. I mean, eventually, next to every sensor, you're going to have a small Akita type processor, very low power that does small compute that gives you what we call region of interest, because I don't want to send all the data over. So if I have a small compute engine that says, okay, here's the region of interest that I'm interested in, now only transfer that data over, because if you have a 4, 5, 6 megapixel camera, you can't be sending all this data. There's just too much bandwidth that you're taking up for 99% irrelevant data. But if you have a small neural processor in there that says, hey, out of this 4 megapixel camera, I only need this 200 by 200 squared. That's my region of interest. So the first model I'm going to use is just say, find what I'm looking for. Now, tell me if it's important out of these 3 classifications. Good. Now send that over to the, the other piece of compute engine, or I may do it on the same engine to do some analytics on it. And then I pass it up to the cloud, because, right now, a lot of these like Ring doorbells are all motion based. So it's sending, think about how much data it's sending up to the cloud when you get 30 seconds of video that was your wind chimes going off. That's the type of thing. But if you're only training it for like dogs and people, that's the only time you'll go, oh, these are the 2 things that are important, but I only want to send people up, and now I have really good data that's important data, and I'm not wasting a lot of the bandwidth in these systems.
Yeah, and I think we need guys like system architects to design these systems and then think of this problem from a from a top level view. And it's only these guys who can really design an efficient system. When you find what products can do, you can really embed an AI accelerator into an image sensor. If that's the use case that requires it, like, hey, I'm having 4K of resolution, but I can't keep sending so much of information. I need some ROI to be done. Then you need to think of a different approach on how do we address that. So to me personally, I think these guys are the most valued people for the coming future, because there's so much that now you have reached the limit of this computation, but now you need to be smarter in almost every domain that you need to do.
And I talk about chip cost, but think about every time you send data up to the cloud, that's cost as well. These Amazon guys don't store stuff and analyze stuff for free. So if I can minimize the amount of data I send up there, it saves me cost on that end as well.
Certainly does. And I was talking to someone in Samsung at a tiny machine learning conference in 2020 in San Diego. And of course, they were thinking point data because the image data was just too hungry, right? Too much throughput to be sending between handset and cloud. And even point data, when it's accumulated in big numbers. A question that I have is on our operational scenarios. We've got a care platform hub team that will be taking care of the actual dashboard, if I can put it like that. They're like your guts of the overall system that we're going to be building. Again, it's fluid at the moment. We haven't really defined exactly the project scope. But beyond that, we have indoor, outdoor operational scenarios. We have in the air and on body. So we're trying to basically capture all the different types of treatments we might have through the applications we may conceive and through eliciting real interviews from people. What do you want a care platform to do, right? So we haven't done the interviews yet, but as you said, Nikunj, we're starting to think right at the beginning here. We're brainstorming, and it's a bit uneasy for the students at the moment. Oh my gosh, this is massive. But we are looking at existing solutions for care. What is out there already? The scope, is it going to be ASU centric, city of Phoenix centric, Arizona, US, global? What kind of care platform? Who is it addressing? Who's our stakeholders and the end user? You know, is it the everyday person? Is it those who are in vulnerable communities? Is it underrepresented minorities? Is it the unhoused? And then we're starting to think configuration. But this question, and because we have all these skill sets in the class, we want to attack this. We have a couple of sci-fi writers in the class, in Chandler and Madeline. We've got Diver, who's public policy. We've got Lance, who's health management from the Management Thunderbird School. We've got Krit and all of Sai and Harish and Kushal and Shriteja and Mason, all from very different engineering / computer science realms. So we're trying to integrate this. And of course, some people will be at the front end of the design process, gathering the data, making sure that we're actually building something people want. But of course, we're only going to get to dip our toes into the machine learning side. That's the best I can describe it, and prototype some very nascent stages of what we visualize. But we hope that at least we're going to have some operational scenarios and use cases that when you come to see our final products, you'll go, okay, the next class, maybe next year, may be able to take the use case scenarios we've developed and implement them more fully and conceptualize the platform and grow it. But that's our hope.
Yeah.
With final minutes, because I know we've gone over time, your time that is, we've got another 15 minutes of class left, but can you tell us some careers? I just want to open it up. Give us an idea of who BrainChip's hiring and the kinds of careers in this space, not just technical.
Sure. Right now, at BrainChip, I'd say we're a small to medium-sized startup. We have about 80 people, and we're hiring people all the time. Now, on the non-technical marketing side, operations side, people that really know how to collect data, how we push data out. And when I say push data out, how do we message to different people? So you saw what we call the hub of our ecosystem, that BrainChip is the center. We're trying to communicate that we're the center of this AI infrastructure. How do you create a social that puts it on LinkedIn, different social media places? Because as a company, we want to spread the word, not just to engineers, but students as well as business people as well. So on the marketing side, it's all about that outward communication, targeted who you want to target your messaging for, and deliver those tracks to those industries via, LinkedIn, via Twitter, whatever. Okay. Now we are a technology company, so there is a lot of technical stuff that we have certain areas, whether that's software engineers, whether it's hardware engineers, the design, whether it's customer facing engineers as well. You got to be able to communicate externally what we do to the right people and have that communication tools to be able to, articulate difficult problems in simplistic manners, because not everyone is a AI expert. Even in, our field, there's a lot of people who design chips that don't know anything about this. We also have salespeople. The salespeople, you do probably need to pick up a little bit of technical side, but that can be learned at least at the top level as well. So, and then HR, there's always HR and finance, those types of positions as well. And I deal with a lot of them, both on the HR, finance, sales, and engineering. And then there was a question about smaller processors and its configurations. So one of the things that's really interesting, when you're doing what we call an applications processor, think Apple, Qualcomm, or Samsung. They're doing the host CPU for phones, selling millions of devices. They can afford to be smaller in technology, to have a lot of compute, and they might use Akita, in that system. When we talk about sensors, whether they're vision, vibration, or what have you, those are generally low-cost dollar parts that are in higher technologies, like 90 nanometer, 65, or 40. So, size really depends on the process that you're going for. And those sensor people are just trying to get 1 or 2 nodes of Akita processing in it that are quite big for those technologies. It's like half the chip will be, an NPU, because they haven't scaled down to have the compute necessary on the digital side that you do on a lot of the digital logics. But once the sensor guys start integrating it in, then you have the other compute guys will follow, so that this overall system's efficiencies get transformed. I hope that makes sense.
Todd, we had one more question. Curious, somebody was direct message to me. Does it cost as much as an Arduino costs, like $100, or are we talking more?
So, okay. So are you asking about the chip or the IP? So generally when someone, I'll give you both. So our current chip, you can buy a card online for about $500. These are the ones we're given to you and your team to use. Now those aren't our cost, but we kind of keep it there to keep the, because we want people to really want to invest in it so they use it. Now, when you're licensing IP and you're building in a chip, as I said, a chip costs 50 to 500 million to make. So you're going to pay millions of dollars to license the technology to integrate into a chip, and then you're going to pay a royalty on top of that. And so, like, if you guys know ARM, they get like an average of 7 cents per chip that goes out that's based on ARM technology. And everyone uses ARM.
Thank you about it. I was like thinking about commercially, if you want to buy outside, like how much does it cost? Like I think I got the answer. Thank you.
So we have several, systems on board, and I think one of the parts of being in the university program, just talk to Katina because we have a highly discounted rate for people in the university program. You have several boards to play with, 2 or 4, we can get you as many as you need. And if you personally want to get one, just talk to Katina and we'll get you one at, I think it's 50% off. So a couple $100, which is under the cost of what it cost us to make these and support them.
Yeah.
We also had a question relating to non-technical careers in this space. You partly answered it, Todd, thank you. But do you ever see the potential to hire people who can do great storyboard design, great journey mapping, affinity mapping, or are they in your client space? That's not really BrainChip space, it's really the client solution. What do you suggest for these people?
So just to let you know, I worked with our marketing person in that train video that you put together. We actually did storyboard that, working with her to figure out what order, what message we're trying to send. That is part of marketing. And you would work with a technical person as well to help build these storyboards that create these great videos that we put together. And then they're getting better and better every time.
Yeah, I think I would definitely vouch for that. I mean, even though I'm technical enough and I understand the technology, but customers, or even when they look at our technology and trying to compare what we offer, it's important to message the right way on how we can benefit our product. So I think folks like those are equally important as the technical guys who are making the product, because engineers will make something, but can it really be implemented on a product? For example, an on-chip learning algorithm. It's exciting, it's new, it's the best out there, but how do we say that, hey, customer A, this is how the on-chip learning is going to help you in your product, and give it as a cutting edge comparing to others? It's something of that person to build a story out of and really create that excitement on putting in simple words that this is what the benefit is, this is what you will get out of it.
And a matter of fact, that's what they did when we created that train video. I sat down with her and I'm kind of saying, here's what it's saying. And I'm not very articulate that way. So she was able to take my words and write them into a script that followed that train demo. And then, they produced it in marketing. So, there's lots of different avenues. You just got to think outside the box and never think there's a limitation, of what you can do. You can be a part of everything. And as you're young, you want to absorb as much as you can, because when you get old like me, it's like, it's hard to learn new stuff.
I had a question about where you guys get your outside news so you can keep up on all of the things happening in the world. So I am non-technical. I'd say I got like 30 to 40% of the presentation, but next time you guys come back, like I'm aiming for 80. So do you have a place where you get your news on like neural network chips, chip developments, tech industry?
So
also, I might have frozen.
Just to let you know, Nikunj is a machine learning AI specialist. He went to school for that. Me, on the other hand, I'm a hardware guy. I didn't know anything about AI. I knew about CPUs and GPUs. So what I did is I went to YouTube and I watched a lot of YouTube videos on CNN's AI for dummies. And, I had a good hardware background, but that's where I go to learn a lot on anything I don't know, because there's enough videos out there. You can figure out just about everything, even complex stuff like this.
I kind of told the students the same. I don't really learn by textbooks any longer. I used to. I like reading papers, academic papers, but YouTube is where you go to get educated. You're going for a walk, switch on BrainChip's videos. You're going, walk the dog, or in transit somewhere, stuck in traffic, long haul drives. Just put it on and make this a daily habit, that you're absorbing information that could be your future work. And if you like it, and you find it interesting, do venture into that space. And my encouragement and thanks to Nikunj and Todd for exciting us today, particularly because I perceive that even science fiction writers in storyboarding and journey mapping are actually technical people. Diver, I know we're saying, public policy students are not technical, but actually you are. If you can comprehend the concepts, you don't have to necessarily be a programmer. So long as you can walk and, the talk and speak what's going on and comprehend it and share it and help others understand what's going on. I think this group has got a lot to give. I am emphasizing, Nikunj and Todd, the beginning part of the process of, sitting down and writing needs statements, sitting down and writing, who are your stakeholders, and doing that mapping to the application context, and then getting the user data where we've got proof, we've got evidence from the field. These stakeholders said they want this, okay, but this is where the technical must meet the solutions advisors, right? The solutions architects meet the solutions advisors, and this is a good group to test this on. But thank you.
So I always tell my kids, nothing is hard once you know it. And it may seem challenging, but long division was challenging at one point in your life as well. You learn a little bit and you retain it, and you learn a little more and you retain it. And that's why you are where you are. You guys are doing extremely well. You're in this class, which is very nice. They didn't even do this when I was in school. So, congrats to you for sticking out 2 hours. That's awesome.
Yes, and they were on before, and we'll just end it here and say a great big thank you from all of us at ASU, our Smart City Infrastructure and Tech course, CSE 598, HSD 598, and to all of you, thank you for coming, and thank you so much to our presenters today from BrainChip Inc.
Okay, thank you.
Thank you so much.
See you, everyone.
Bye-bye.
Bye.
Bye, everyone.